Hello, welcome to the first lecture for the Mathematics Class 11, Chapter 8, Sequences and Series. So, for this chapter, what we will be looking at is how are sequences represented, and what are sequences and what are series. Okay, and we will try to see how certain examples with respect to these can be so what is a sequence? Okay, so in the literal sense, sequence means that there is a pattern which is followed. Okay, so okay, so sequence is say items ordered. Okay, are presented in a certain order or pattern. Okay, so there is a certain logic or a kind of some pattern that is followed when we consider something to be in a sequence. Okay, so it means that it's a collection of things that is ordered in such a way that it has an identified a first item, then a second item, or first member, second member, third member, so on. Okay, so there will be something as A0 as your first item. Okay, and the second one that is there. Okay, or the third one. So there is supposed to be a relation between these two. Okay, a relation exists between A0 and A1, and between A1 and A2, a similar relation will be there. Okay, a similar relation as in the relation that is there for A0 between A0 and A1, a similar relation has to be followed between A1 and A2 and so on. Okay, so this is how it is done. Now, what are some kind of examples that we can see is in case of real life examples. Um, the kind of the if you try to find the increase in certain kind of quantity. Okay, so over the number of years, how how certain quantity has increased. Okay, or for example, how the population of say human beings or any other species can form a sequence when you try to calculate, or you try to have the number of species that are living at a certain time, and then again when you take it at a different times, there will be a sequence that is formed. Okay, there will be a certain rate of increase or decrease or whatever. Okay, so when you present these things in kind of like a ordered form, it can be called a sequence. Okay, so this is what we can understand by the term sequence. Okay, so you can say that for in case of sequences and series, so sequence can be called as a list of items or objects presented, or presented slash arranged in an ordered or sequential manner. Okay, so with respect to sequences, so there will be only a list. Okay, so you have A0, A1, A2, A3. Okay, So this is so on. Say the sequence only exists up to, it has only say 10 terms. Okay, so now since we are saying that it is starting with 0, so the last item of this sequence would be A9. Okay, because we are saying there are only 10 items in this sequence. Okay, suppose this is what we have to get. Okay, so there are 10 items in this sequence, so you can denote each item as A and some number. So if since it's starting with A0 and there needs to be only 10, so there will be A9. Okay, so this is what is a sequence. Now, what is a series? Okay, so in normal terms, even series, sounds like something that is arranged in a kind of an order. Okay, but the series actually, in terms of arithmetic, okay, in terms of what we use in mathematics, is actually the sum of all the terms in a sequence. Okay, so now we are calling, or we have got another term that is series, and that is actually the sum of all of the terms in a sequence. Okay, but this sequence can be a series only if it only if the terms have a definite relationship among them. Okay, only then can we will call the sum of such terms in a sequence as the series. Okay, so this is what we have to understand when we are talking about your are sequences and series. Okay, so now sequences, as we are telling, we are calling it a list of items or objects. So in terms of sequence, we can have a kind of any quantity that can be presented. Okay, quantity or quantitative in nature. Okay, so it is quantitative in nature. So that means mostly we'll have arithmetic types of sequences. Okay, so arithmetic, so that means mostly we'll have numerical relations. Okay, numerical relations. Even if you take like a statement like um, say you have to find how many generations are there for somebody, or across 30 years of somebody's life, or you have to go back to 30 generations. Okay, so there those things can be represented in a numerical form also. Okay, so that is what we understand as sequence. So suppose have the arrangement. Okay, and there is a particular order. Okay, you have objects arranged in a particular order. Okay, so these can be objects or a set of values. Okay, so you will have A1, suppose A2, A3, A4. Okay, and all these actually the the numbers up to say an anything. Okay, so n is the last term, okay, or the last position. Your an is the last term of the sequence. Okay, and you will suppose have ai. Okay, so I going from 1, 2, 3 all the way up to n is the position of the term. So you can be asked, find the, say, 10th term of the sequence. So you will have to find A10 or say A12 or A15. Okay, so on. You can have, all these kind of terms. Okay, listen until you reach, say, N. Okay, so now there are two types of, sequences. So you can have types of sequences. Okay, so you can have either finite or infinite. Okay, so what do you mean by finite or infinite? Okay, so finite is that you can have only extends up to a certain term. Okay, so there is a limit to how many terms we have. So if you are, for example, we'll do the example in the next slide. And infinite is the that means that there is no limit on number of terms in the sequence. Okay, only up to certain term in the sequence. Okay, so for example, in finite, suppose you are asked, write the sequence of even, say, let's format sequence of the first 10 even numbers. Okay, so in that prospect, what we get is then the sequence is, so the first even number that we have is 2. Okay, the next will be 4, 6, 8, 10. Okay, so these are what 5 has been done. You have 12, 14, 16, 18, 20. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now this becomes your finite sequence. Okay, now infinite, as you know, that there is no limit. Okay, so no matter what you do, so if you are asked to write the sequence of all positive real numbers, okay, so it will start with say 1, and it can extend up to infinity on the positive side of the real numbers. Okay, so that is how you can have your finite and infinite series. Okay, now you will have to, there are a few different types of sequences, okay, or examples you can say. So we'll just write the common, we will see more, examples and conceptual understanding of some of these sequences in the later classes. Okay, so for now I'm just like, introducing them over here. Okay, common examples of sequences. So the first one that we have is called arithmetic. Okay, so in arithmetic, what happens is that every term, okay, that is existing in the sequence is, created by adding or subtracting one one number. Okay, so there is one particular number which will be either added or subtracted to the previous term. Okay, to the previous term, so you get the new consecutive term. Okay, so this can be written as every term okay, is created by adding or subtracting a definite value or a number to the previous term of the sequence. Okay, so you can easily understand. If you take even this example for that matter, okay, so over here, you can see if you take the example of 2, 4, 6, 8, 10. Okay, suppose this is a sequence. You can see why this would be called an arithmetic is you can have 2 as the first member of the sequence. So you have 2. Okay, and then if you add 2 to it, you get 4. Then if you add you know uh, 2 more, okay, or 2 again with the 4, the new term will be 6. Okay, similarly, if you add 6 plus 2, you will get 8. Okay, so you can see that the specific number that is being added is 2, okay, to each and every term, and then you get the next consecutive term. Okay, so that is why this is called an arithmetic sequence. Okay, now the next one that we have is geometric sequence. Okay, now similarly in arithmetic, what we did, we either add or subtract. Okay, so in geometric sequence, we actually get the new terms by multiplying or dividing a certain number. Okay, from dividing or multiplying by a certain number with the preceding number. Okay, with the previous number in the sequence. Okay, so that is called a geometric sequence. So you can write this as every term is obtained by multiplying with or dividing by a, a certain number with respect to the previous term. Okay, so suppose you have, for an example, you can have 2. Okay, suppose this is your, sequence. So over here, you can see that this is your first term. Okay, so you have 2. So if you have multiplied 2 by 2, you get 4. And if you multiply 4 with 2, you get 8. Multiply 8 with 2, you get 16. And if you multiply 16 with 2, you get 32. Okay, so you see that the term that is being multiplied repeatedly, okay, is 2. Okay, and therefore you get a sequence of the form that every term is created by multiplying the previous term of the sequence with 2. Okay, so this is a geometric sequence. Now the next one is a harmonic, okay, sequence. So now, as in the previous two, we saw, okay, you either add or subtract, for arithmetic sequences, and you multiply or divide with respect to, your geometric sequences, any number. But your harmonic sequence, okay, is actually, a kind of a list of numbers if the reciprocals of all the terms of the sequence forms an arithmetic sequence. Okay, so harmonic sequence is actually more of a series. Okay, It is a series of numbers where the reciprocal of all the terms of the sequence form an arithmetic sequence. Okay, so this means that only if the reciprocal of the terms of the the series of numbers can be called a harmonic sequence only if the reciprocals of all the terms of the sequence themselves form an arithmetic sequence. Okay, so this is a bit more complex in nature. So we will see some examples of it in the later classes. So it will be easier for you to understand when we have dealt with all the concepts of arithmetic sequences, and also finding out how we can find series. Okay, with respect to sequence. Okay, so let's see another one. So there is a unique sequence. Okay, so this sequence is called Fibonacci sequence. Okay, so Fibonacci sequence, it's a different, or it's an interesting kind of, uh, you can say, about a series, or a different kind of sequence. Okay, so where there is a recurrence of relation that happens. Okay, so now the previous ones we saw, there was a particular number being, added or subtracted or multiplied or divided by. Okay, so there was one particular number. Okay, if you found the number, you can easily just multiply that with all the with the previous terms to get your sequence. But in Fibonacci numbers, uh, only if you have the kind of, there's a different relation that is, taken into consideration. Also, the relation itself. Okay, for arithmetic sequence, we saw that number stays constant. Okay, with, the relation stays constant between the two terms. But in Fibonacci sequence, that actually does not happen. Okay, so this means this actually has no visible pattern. Okay, Fibonacci sequence can be written in the form of 1, 1, 2, 3, 5, 8, and so on. Okay, so this is actually the Fibonacci sequence. Now over here, if you just look at it, directly, you will not find any visible, kind of, say, a visible relation. Okay, a visible pattern that is being followed. As you know, when you could say for 2, 4, 6, 8. Okay, so you have very easily. Okay, you can find. Okay, so over here, your first term was, 2 into 1, say, and the second term was 2 into 2, and you have 2 into 3. Okay, so either as the, kind of the logic that I had explained in the previous one when we were doing arithmetic, that if you multiply 2 with the first term, you will get the second term. Then again, if you multiply 2 with your second term, you get the third term. Okay, or you can also see that if you multiply all the consecutive, natural numbers with 2, that is how you will get this sequence. Okay, so this is 2 into 4. Over here, you can see that the number 2 is being multiplied consecutively to the all the natural numbers starting with 1. Okay, so this is also another way that you can explain the pattern. But for Fibonacci sequence, as you can see, that there is no certain the pattern is not very easily visible or decipherable. Okay, so but this is a sequence. Okay, so how is the sequence actually found? So suppose you also enter another term over here starting with 0. Okay, so suppose these two are the first term. So what you get is actually, you know, suppose this is your A1 and this is your A2. Okay, so your A1 is equals to 0. Okay, and your A2 is equals to 1. Okay, so these are, suppose, you are asked to make a sequence out of this. So what you can do is, like, if you add A1 and A2, okay, to get A3. So this will be 1 again. Now suppose you take A4. Okay, so A4, how can you, understand if you can, how do you get A4? If you add your A2 plus A3. Okay, so what was your A2? Your A2 was 1 and your A3 is also 1. And then you get 2. Then if you are asked to get A5. So you see over here that we have multiplied, we have added the previous term, then the requested term, and also the term before the that previous term. So over here you will get A5 is equals to, say, A4 plus A3. A4 is 2 and A3 is 1. So you get 3. So you can see that this is how the sequence is being formed. Okay, so in general form, so for Fibonacci sequence, there is a general form which you can, put. So that is your AN should be equal to AN minus 1 plus AN minus 2. Okay, so the nth term of the Fibonacci sequence is going to be the sum of the two previous terms. Okay, two previous terms. Now over here you can see that for an is equals to an minus 1 and n minus 2. Okay, anytime your n has to be more than 2. Okay, so over here, obviously, for A, there is no, A0. Okay, A0 does not exist over here. Okay, so A0 does not exist. So we have to consider either A1 as equals to A0 and A1 is equals to 0 and A2 is equals to 1. Okay, so this is called a Fibonacci sequence. Now we understood, obviously Fibonacci sequence is a special kind of sequence. Okay. Now, suppose you have another kind of a sequence. Okay, so there is no arithmetic logic that could be found in it, or you might not get an easy formula to describe that sequence. So you can assume, okay, that suppose you are asked to write the list of prime numbers. Okay, so so the list of prime numbers that we have is 2, 3, 5, 7, 11, okay, etc. So over here you can see there is no exact formula for the nth term of the sequence. Okay, because over here there is, not really, because even if you add 2 plus 3, you do get 5, but if you add 5 plus 3, you will not get 7, you will get 8. Okay, so you can see that there is no, it's not that easy to find the relation or the pattern in such kind of sequences. So such sequences can be only, given with respect to a verbal description. Okay, so sometimes it's not ideal situation, or it's not even practical to have sequences in all kind of terms. So what we can say is that sequences, okay, sequences can be regarded as a function whose domain is the set of natural numbers or some subset of it. Okay, why do we say this? That, because some sequences cannot be given by a specific formula, but you can still have them arranged in a sequence. Okay, so the example is sets of prime numbers. Okay, so this is the sets of prime numbers. Okay, so in prime numbers, you can write it in terms of A1, A2, A3, A4, up to AN. Okay, so that is why you can, for sequences, you can use the notation of AN. Okay, where this N is actually natural number, or for AN. So this is what we understand. Okay, so now we have seen the kind of introduction or basis of different kind of sequences. Now let's see what are the differences between your sequences and series. Okay, so we have described series as the sum of the terms. Okay, so sequences, list, series, sum of terms, list of terms. Okay, so if you try to understand the different or the differences between sequences and series. Just excuse me a moment, I'll have some water. Okay, so you have sequences and series. So the first point of distinction between them is sequences are a set of terms that follow a pattern. Okay, whereas a series is the sum of the terms of the sequence. Okay, now the next one, as we can understand, is the order of the terms of a sequence. Okay, so the order of the terms in which the sequences, represented or sequences written as is important. Okay, so if you arbitrarily just write a sequence, it won't be very you won't be able to understand the pattern or the relationship that exists between the two terms easily. Okay, so the order in which a sequence or the numbers in a sequence are going to be written is important. But with respect to series, the order of the terms is not so important. Okay, that means, like, suppose we have to write it in terms of 2, 4, 6, 8. Okay, this cannot be represented as, say, 6, 4, 2, 8. Okay, this is not how we can write. Okay, this is not acceptable. This is how we write the order of the sequences. But suppose the sequence is, the sequence is 2, 4, 6, and 8. Okay, so the series for this would be, the sum would be 2 plus 4 plus 6 plus 8. But no matter in which position you write the individual terms, okay, so the answer would be the same. So what would be the answer here? So if you have 2 plus 4 is 6, 6 plus 6, 12, 12 plus 8, so this is 20. Okay, so even if you write it in terms of the one that we saw here, okay, so if you write it as 6, sorry, okay, so you have 6 plus 4 plus 2 plus 8, this would still be the same, because 6 plus 4 is 10, 10 plus 2, 12, 12 plus 8 is again 20. Okay, so we can see that in terms of, writing a series or explaining a series, the order of the terms are not necessarily important. Okay, now you can have, these are the two, main differences in series and sequences. But when we have, if we have a finite sequence, okay, so for example, we have 1, 2, 3, and 4. Okay, we have 1, 2, 3, and 4. So this will, correspondingly give you a finite series. Okay, so that would be what? 1 plus 2 plus 3 plus 4. But if we have an infinite sequence, okay, so that is 1, 2, 3, 4. Okay, this will also have, okay, so there will be no dots here, sorry. Yeah. So this is a finite sequence. Okay, so this only extends from 1 to 4, and then the corresponding series would be a finite series itself. Okay, so you have 1 plus 2 plus 3 plus 4. But for infinite sequence, you will have an infinite series, because as the number of terms, keep increasing, those newer terms will also be, summed together. So you'll have 1 plus 2 plus 3 plus 4 and so on. Okay, this will go on increasing. Okay, so this is what we understand by, the definition of sequences, and also definition of series, and how the series is actually being done. Now let's take a few examples where we will see how it actually comes into the play. So for example, okay, you are asked, say, suppose you are given that a person ancestry has 30 years of generation gap. Okay, so how do we find the number of ancestors? Okay, the ancestors that the person has had in the last 300 years. Okay, so suppose you are asked, like, how can we find the number of ancestors that the person has had in the last 300 years? Okay, so if we try to see, okay, so how many generations would this person have had? Okay, in the past 300 years, if every generation has a gap between them of 30 years. Okay, so you can get the total number of generations, okay, as 300. So the total years, or the number of years that we are being asked, and the generation gap, so that is going to be 10. Okay, so the person has had 10 sets 10 generations. That means 10 sets of, ancestors. Okay. So now in every generation, there must be a certain number of ancestors that have been present. Okay. So suppose generation, your first generation. So where we are trying to, calculate that maybe these were the first ancestors of the person that we are talking about. So for the generation, to start, you will need two people. Okay. And then with respect to the second generation, okay. So the second generation, now this person can have, say they might have, multiple kids. Okay. It's not necessary that they'll have only one or two kids. So they might have plenty, number of kids, but the person that we are, trying to find the, ancestors of, that person can be, can be tracked down to only one of the, one of each child of the first generation. Okay. And that person will have to be, will be reproducing the next set of kids, okay, with another person. Okay, so the total that you can understand is that in the next generation, okay, you will still have the two from the first, and you will have two more people. Okay, so you have 2 plus 2, 4. Okay, so in that case, you will have to, actually, it's supposed to be 2 into 2. Okay, so that is how, it will get multiplied and it will go on increasing. Okay, so in that case, your sequence, okay, that is going to exist is going to be 2, then 4 into 2, 8. Okay, so how is that happening? That one person from the first generation has to, get, has to reproduce another person, okay, in the next generation. But the other two will also be there. Okay, so in the second generation, the number of ancestors would be 4. Then similarly, again, it will, go on increasing, because as and when your generations increase, your reproducibility also is increasing. Okay. So this is a type of a sequence that you can form. Okay. So over here, you can see that your A1 is 2, A2 is 4, A3 is 8. Okay. And all the way up to your A10 would actually come out to be, if you keep multiplying up to the, 10th, uh, 10th, or if you keep multiplying 2, okay, up to the ninth term, the 10th term that you will get is, if you go on increasing, or if you go on following the pattern, you are going to get 1024. Okay, now this is actually an example of finite sequence. Okay, so this is an example of finite sequence. But suppose you are asked, okay, to say, find the quotient. Okay, find the subsequent quotients for every time we divide 10 by 3. Okay, so find the quotient at every step of the division of 10 by 3. Okay, so if we, kind of start dividing your 10 by 3. Okay, so at the first step, you can write 3. So 10 minus 3 is, 10 minus 9. Okay, so 3 into 3, 9. So what you get is 1 over here. Okay, so the first term is 3. Okay, now we go on for the, the next step of the division. So you add a point over here, since, you have remainder 1. So you get a 0 again. Again, you will multiply, again you will get 3 in the, 0.3 in the quotient. So you'll have 1. So the next term would be 3.3. Then again you have 1, so you again try to get a 0 over here, and the next quotient would be again 3.33. Okay, because we are asked to find the quotients of the division process of 10 divided by 3 at every step. Okay, so then you will see that the sequence that comes up to is 3, 3.3, 3.33, and similarly it will actually go on, okay, with 1 3 adding to the the after the decimal points. Okay, and you will see that this will go on increasing. Okay, if we keep uh, if there is no limit to how many times we are dividing 10, or how many steps we are taking, okay, at order to which point we are going to stop dividing this 10 by 3, so the number of questions can go on increasing. Now this can be then actually be termed as your infinite sequence. Okay, so these are kind of an example of finite and infinite sequences. Okay, so we have already seen that. So let's take some examples. Okay, so simple examples, not very tough in that manner. Oh, sorry. Okay, so let's see the question that would can be asked is, if 4, 7, 10, 13, 16, okay, is a sequence, find the next 4 terms. Okay, so over here you have 4, 7, 10, 13, 16. Okay, so let's first see if there is this is a kind of an arithmetic sequence, or a geometric sequence in that sense. So over here, if we A2 minus A1, okay, what would you get? You get 3. Now you see, if the same number is or the same result is presented if you if you subtract A3 by A2, and that again it will become 10 minus 7, so that will be 3. Okay, and if you see the sequence carefully, you will see that there is a difference of 3 from the the uh, presiding term and the consecutive term. Okay, so therefore, if your 16 is the last term that is there, that is given, and we are supposed to find the next 4 terms, so you can add 16 plus 3. Okay, so you'll get 19. Then 19 plus 3 would be 22. 22 plus 3 would be 25. And you have 25 plus 3, that is 28. Okay, so your the next 4 terms are 19, 22, 25, and 28. Okay, so this is how we can find out to see what is the next term that we have. Okay, so for now we are only dealing with easy examples to understand what exactly goes on when we are trying to have a sequence. Okay, suppose the next is, you have 1, 5, 25, 125, and 625, and so on, is a sequence. So let's find the next 2 terms. Okay, now over here, if you want to see if it's an arithmetic, sequence, you can just subtract the second term with the first term, you will get as 4. And if you do that with your the next two terms, so 25 minus 5, you'll see that this is not being followed. Okay, so this relation is not there is no particular relation if we just do the subtraction of the between the terms, between two consecutive terms. Okay, so but obviously you can see very easily that there is a pattern that is being followed. So what is that? That is 1 into 5 is going to give you 20, is going to give you 5. Okay, and then with your 5, if you multiply 5, it will be 25. Okay, and then 25 into 5 is going to give you 125. Okay, so you can see that there is a pattern being followed. Okay, where each and every term is actually getting multiplied by 5 to get the next term. Okay, so the term that we have in the last place over here is 625. So multiply 5 with that. So you get 5, 5 to 12, 1. So this is your 3, 2, 2, 5. Oh, sorry, this will be 3, 1, 2, 5. Yeah. Okay, so you can see that the the way that we get the term is that we multiply. Okay, we have already seen that by multiplying the terms with 5, you will get the next term. Okay, so what would be the next term? Now we have been asked to find the the next two terms. So we got one of the next terms after 625. So now you multiply 3, 1, 2, 5 into 5. Okay, so that actually comes up to be 5, 2, 6, 5, 1. Okay, so you get 15,625. Okay, so 15,625. So these are the next two terms of a sequence like this. And now over here, you can see that since we are multiplying the terms with a certain number, this can also be, an example of a geometric sequence. Okay, so this is, kind of how we have different kind of sequences. Okay, so in the next class, we'll move further with sequences and we'll see a few more examples and so on with the chapter. So thank you for attending.